This video explains compound compression refrigeration systems. These systems use multi-stage vapor compression, dividing the compression process into multiple steps to improve efficiency and performance, particularly for applications needing large temperature differences. This presentation will cover the following compound compression arrangements: two-stage compression with liquid intercooler, two-stage compression with water intercooler, two-stage compression with flash chamber. First, let's examine two-stage compression using the liquid intercooler. The diagram illustrates the layout of the compound compression system, which includes various components. In the diagram, you can see a low-pressure compressor, a high-pressure compressor, a condenser, a liquid intercooler, two expansion valves, and an evaporator. In this system, the liquid exiting the condenser cools the refrigerant from the low-pressure compressor by mixing with it after passing through an expansion valve, which lowers its pressure. Next, the refrigerant vapor formed is directed into the second stage of compression, the high-pressure compressor. The wet vapor from the intercooler is then expanded to the lowest pressure and passed through the evaporator. Now, let's analyze the pressure enthalpy diagram for a refrigeration system using two-stage compression with liquid intercooling. First, the refrigerant is isentropically compressed from saturated vapor at point 1 to superheated condition at point 2 in the low-pressure compressor. Superheated vapor from the low-pressure turbine is cooled to saturated vapor by mixing with liquid refrigerant after it expands from the first expansion valve. During this process, some refrigerant is further expanded through the second expansion valve to evaporator pressure. The cooled refrigerant undergoes a second isentropic compression in the high-pressure compressor, reaching point 4. Condensation occurs from point 4 to point 5, with the condenser exit assumed to be in a saturated liquid state. The refrigerant exits the second expansion process and flows through the evaporator from point 8 to point 1. Let's explore how to estimate the refrigerating effect, compressor work, and COP for this type of refrigeration system. We must first establish the mass flow rates through each component, as they differ from those of a single compression system. Let us consider that M1 is the mass of refrigerant passing through the evaporator in kilograms per minute, M2 is the mass of refrigerant passing through the condenser in kilograms per minute, and M3 is the mass of refrigerant evaporated in the intercooler in kilograms per minute. The mass of the refrigerant compressed by the high-pressure compressor should equal the sum of the mass from the low-pressure compressor and the mass evaporated in the intercooler. That is, M2 is equal to M1 plus M3. Consequently, we can write that M3 equals M2 minus M1. We can express the energy balance in the intercooler with the following equation. M2H5 plus M1H2 equals M1H5 plus M2H3. It is important to note that H5 is written as HF5 because the refrigerant at point 5 is in a saturated liquid state. Additionally, the enthalpy values at points 5, 6, 7, and 8 are the same. The mass of refrigerant, M2, that is compressed in the high-pressure compressor is determined as follows. Using the equation for M2, we can then determine the mass of refrigerant evaporated in the intercooler, M3 as shown here. The refrigerating effect is determined as RE is equal to M1 into H1 minus HF5. The total work in both compressors, WC, is equal to M1 times H2 minus H1, plus M2 times H4 minus H3. If we denote the refrigerant mass flow rate in kilogram per minute, the refrigerating effect, and the compressor work have the units, kilojoules per minute. In the refrigeration industry, the the standard unit is the ton of refrigeration, TR, where 1 TR equals 210 kJ per minute. To convert a refrigerating effect from kJ per minute to TR, divide the value in kJ per minute by 210. Now, let's examine the two-stage compression system with a water intercooler. Here, the refrigerant is cooled by water after initial compression as shown in the diagram. Let's examine the processes on the pressure enthalpy diagram. In the low-pressure compressor, the refrigerant is compressed from saturated vapor at point 1 to superheated vapor at point 2. Then, the superheated vapor is cooled by the water cooler to point 3. The high-pressure compressor then compresses the cooled vapor at point 3 to point 4. The condensation occurs at constant pressure from point 4 to point 5, at a saturated liquid state. Refrigerant expands from condenser pressure to evaporator pressure between points 5 and 6, followed by constant pressure heat absorption from point 6 to point 1. Complete de-superheating to saturated vapor is impossible in water intercooling because the cooling water temperature is not low enough for complete de-superheating of the refrigerant. Now let's examine the refrigerating effect, compressor work, and COP of this system. You can readily notice that the compressors, the condenser, and the evaporator share the same mass flow rate. The refrigerating effect, RE, equals M times H1 minus H6. The compressor work, WC, equals M times H2 minus H1 for the low-pressure compressor, plus M times H for minus H3 for the high-pressure compressor. Then the coefficient of performance, COP, equals refrigerating effect, RE divided by the total work for the compression, WC. Let's now examine the two-stage compression refrigeration system with a flash intercooler. This refrigeration system, like others, features low and high-pressure compressors, a condenser, a two-step expansion process, and an evaporator, as illustrated in the diagram. Additionally, it has a flash chamber. The flash chamber separates the refrigerant vapor formed during the first expansion process, and mixes it with the exit stream of the low-pressure compressor, reducing its temperature closer to the saturated vapor point before feeding it into the high-pressure compressor. Let's examine the representation of different processes on pH diagram. The saturated vapor refrigerant at point 1 is isentropically compressed to a superheated state at point 2 in the low-pressure compressor. Next, superheated vapor discharged from the low-pressure compressor mixes with flash vapor originating from the flash intercooler of the flash chamber, lowering the temperature and achieving state 3. Then, the superheated vapor closer to the saturated state is compressed to point 4 in the high-pressure compressor. Condensation occurs from point 4 to point 5, ideally reaching the saturated liquid state. Subcooling the refrigerant, however, can further increase the refrigerating effect. Next, the liquid refrigerant undergoes the first stage of expansion from point 5 to point 6 and enters the flash chamber. The liquid refrigerant from the flash chamber is then expanded to the evaporator pressure from point 7 to point 9. Refrigerant evaporation, or heat absorption, occurs from point 9 to point 1. Let's examine the refrigerating effect, compressor work, and coefficient of performance. Consider M1 equals mass of vapor refrigerant passing through the evaporator. M2 equals mass of refrigerant passing through the condenser, or the high-pressure compressor. M3 equals mass of vapor refrigerant formed in the flash chamber. We can see that M2 is equal to M1 plus M3. Now let us consider the thermal equilibrium of the flash chamber. M2H6 equals M3H8 plus M1H7. Since M3 is equal to M2 minus M1. M2H6 is equal to M2 minus M1 times H8, plus M1H7. By simplifying, we obtain M1 as M2 times H6 minus H8, divided by H7 minus H8. Refrigerating effect RE equals M1 times H1 minus H9. The compression work WC is M1 times H2 minus H1, plus M2 times H4 minus H3. The coefficient of performance is calculated by dividing RE by WC.